Hi everyone, I'm Alita.
And I'm Teresa.
And we're Form 5 students from the Diocesan Girls' School. We'll be your docents today on this tour of the Hall of the Cosmos at the Hong Kong Space Museum. We're going to start with the Elements in Time exhibit, which displays the abundances of different elements in different time periods and environments. Here, we'll take a look at how the universe became filled with the different elements as we know today, and why they exist in these various abundances. Right after the Big Bang, the universe was extremely hot and dense, and filled with only neutrinos, quarks, and electrons. As the universe expanded and cooled, these came together to form protons and neutrons, which then formed hydrogen nuclei, then deuterium to form helium nuclei. The process lasted for around 20 minutes. Then the universe was too cold for the protons to continue to join together to form new nuclei. At this stage, the universe is filled with the nuclei of light elements, with 75% being hydrogen and around 25% being helium, which is what we see here. Then how did the other 91 naturally occurring elements come into being? Well, a famous quote from Carl Sagan says, "We're made of star stuff." That for stars to maintain their shape and balance the inwards gravitational pressure, they generate radiation pressure through nuclear fusion, which is where two light nuclei merge to form a heavier nucleus and release energy due to a slight decrease in mass. After burning through its hydrogen fuel, it becomes a giant star and then starts to fuse heavier elements like helium, carbon, neon, oxygen, silicon, and on and on. The heavier a star is, the heavier the elements that it can fuse are. However, nuclear fusion hits a wall at iron. This is because nuclear binding energy peaks at iron and then drops slowly for the heavier elements. That means that in all the previous fusions, there is a net energy released, but to fuse iron, there's a net energy consumed. What happens then? Well, elements that are heavier than iron are formed in the later stages of stars instead, either through the slower S process, which happens inside old giant stars, or through the much faster R process, which happens inside supernovae or neutron star collisions. In both cases, atoms gain neutrons and form heavier elements. These explosions in the latter case also expel particles into space at high speeds, where they eventually make their way into us and all these metals and stuff that we see here now. Despite all of this, hydrogen and helium still maintain the highest abundance, just because it is so much more complicated to create the heavier elements. However, we can imagine over a long period of time, those two columns will slowly drop and the others will rise slightly, but not by a lot, because after stars reach the ends of their lives, hydrogen and helium become locked up inside their cores.
Aforementioned supernovas would eject particles of high energies. However, supernovas occur thousands and millions of light years away from us. Can you imagine masses of these particles reaching us right now? Spoiler alert, this cloud chamber here allows us to see the remnants of supernova.
This is called a cloud chamber, and it helps us visualize ionizing radiation. The bottom of it is cooled with dry ice or liquid nitrogen, while the top is exposed to room temperature, creating a temperature gradient in which the alcohol vapor inside is at a supersaturated state and at the very brink of condensing. When charged particles pass through the chamber, it can rip electrons off of its neighboring alcohol molecules, creating nucleation sites, since the charged alcohol molecules will attract each other and condense to form a visible trail.
So what are these charged particles? Well, most of them are cosmic rays, and they're mainly sourced by supernovas in our galaxy. When particles are exposed to the shock wave caused by supernova, it causes the first order of the Fermi acceleration, which is also known as diffusive shockwave acceleration. It allows particles to gain immense energy and travel far distances. Ultimately, they would reach Earth, penetrate through our infrastructures, our bodies, and this cloud chamber here.
If we wait a little bit, we'll see these cloudy white trails forming in the vapor. These are the paths of the charged particles. So how can we tell what these particles are? Firstly, you can look at the thickness of the trail. Particles with higher ionizing power can ionize more alcohol molecules around it, thus creating a thicker and denser trail. Next is the length of the trail. Particles which are lighter, such as electrons and positrons, are easily deflected by collisions, while the heavier muons aren't and can continue on its path to create a much longer trail. So, what do these all have to do with our daily lives? These seemingly invisible particles all around us can actually impact us quite heavily in rare cases. Our computers are made with transistors, which represent 0 or 1. When charged particles hit the transistor, it can flip the bits, causing what's called a single event upset, or SEU, a type of soft error in the computer. This is actually a pretty serious problem, especially in aerospace, and so now all important computers in spacecrafts or planes have backup systems in place to avoid this kind of error. Scientifically, this is also really significant because it's helped us find particles beyond protons, neutrons, and electrons, including the first antimatter particle. In 1932, scientists discovered a particle that formed a trail similar to that of an electron, but curved in the opposite direction inside a magnetic field. This was the anti-electron, or called positron. Muons were also discovered in this way, and this has opened up the field of particle physics, which we'll now talk about in the next exhibit.
Delving into particle physics, scientists have built a gigantic racetrack, which is also known as the Large Hadron Collider, for colliding protons together. These two levers here mirrors the acceleration of proton beams in a real-life LHC. Millions of protons are accelerated close to the speed of light before colliding with each other. So, how do these proton beams reach such insane speeds? Well, it all begins with two main systems. The first one being superconductive radio frequency cavities, which creates an oscillating electric field. When protons pass through this field, energy from the field is transferred to the protons, allowing them to gain immense energy and speed. While the second one being superconductive electromagnets that are used to steer and focus the trajectory of proton beams, allowing them to collide at the desired point. Under the normal circumstances, as stated by the Ohm's law, anything that conducts electricity will eventually lose energy. However, notice how these two systems share the same word, superconductive. The superconductive state is only persistent when the temperature is extremely cold. It's like unlocking fever mode in the game because fever mode only persists during special circumstances. So during this fever mode that is called the superconductive state, it allows the systems to disobey the Ohm's law, making them extremely energy efficient as they will only lose minimal energy whilst conducting electricity. The system also displays a randomness factor, whereas a phenomenon may or may not be produced depending on the panels the ball hits as they tumbles downwards. This occurs because the interception of new phenomena is inherently difficult, as well-known collisions, like well-known data, can interfere with the interception of new ones. The system is also currently at a cooldown as it prepares itself for the next run. Given that superconductive systems are extremely cold, it takes around 1 to 2 weeks for them to reach room temperature again before it's available for the next use. One of the major discoveries found using the LHC is the Higgs boson. It's related to the Higgs field that gives mass to other particles. However, the boson's own energy, own mass, remains a mystery. Though we'd love to continue, we'd hate to say that this is the end of our tour. However, the discovery of the universe is infinitely endless, and we'd hope to see you again. Thank you.